Oh, little Flo, I love you so, especially in your nightie. When the moonlight flits across your tits, oh Jesus Christ almighty.
Greetings, the Astro 30 here, and welcome to another video. Today, it's been a long time coming, but I was going to re-look at this, but we're going to look at an OpAmp based power amp. Now this one should produce a lot more higher power than the previous version that I was messing around with, mainly because we've got two separate VCC and VEE lines respectively. The output stage using a higher current one. Now, I'll put a link in the description below to the first power amp that I was playing with, just so you can check that out. Now, I will warn you ahead of time that this may end up being quite a lengthy video, so get some popcorn, sit back, get a few cigarettes, a few beers going, whatever, and enjoy the show. First off, this is the design that is available on Rod Elliott's Sound Pages site, and it's actually a reader contribution to his project pages. It's by a guy named Rohit Balkishan. Don't ask me to pronounce that again because it's probably wrong. What he's done is a basic simple topology here. We've got an op-amp here which is then driving an output stage, and the feedback loop is, or the global feedback, negative feedback, is part of the two. So the feedback comes from the output stage and goes back to the input stage. So basically this op-amp is being used as a voltage amplifier. Now there is one interesting thing about this circuit. Now, ignoring the input stage here for a second, we're looking at the output stage from this point onwards. Notice how the output of the IC here is going to the base of this second compound pair. This is in C clay E or complementary feedback pair configuration here. But we'll notice that the output is going into this transistor here and not between these two diodes, as we would commonly expect to see in a power amp that's designed using an op-amp. Usually the op-amp output is connected directly between these two diodes. In this case it's not. But it may look strange to some people, but if you think about it logically, it does actually make perfect sense. What do I mean? Well, let's have a quick look at the whiteboard. I've redrawn the output stage on the whiteboard here. For clarity, this is our output point. And really there should be a couple of degeneration resistors in between these two collectors to help prevent thermal runaway. But they're not in the original schematic. I might be adding them, and they only need to be something like, you know, 0.22 ohm, something like that. Anyhow, I've simplified it by removing the capacitor that was across this biasing network, and I've just drawn the potentiometer and the fixed resistor as two resistors, and there's a reason for that. I'll get to that in a second. But if we look at this topology, what is missing down in this area? Anyone? Now, well, if you think about it like a normal discrete power amplifier, what would go down here? That's right. The VAS, or voltage amplification stage. So basically our op-amp as badly drawn as that is, OpAmp is mimicking, for all intents and purposes, the VAS circuit. So that's why the input entry point is down here. It's exactly the same. Now, of course, the topology can be flipped. So you've got a PNP transistor up here and you're biasing down here instead, but it's essentially the same, except this will be a PNP transistor up here as opposed to an NPN down here. But basically that's what it is. We've got an output stage with a VAS at the front. So why have I got these two fixed resistors? Well, we can also do something known as bootstrapping. We can take an electrolytic capacitor between those 2 points, which now becomes a voltage divider, and connect it to the output. And what that does is it gives the output stage, or at least the drivers anyway, a constant current source in simplicity terms. There's a video by John Audio Tech on YouTube that does actually explain bootstrapping pretty well, and I'll put a link in the description down below to that. But this is the things I'm going to try. One, I want to get rid of that potentiometer, that 50k that he's got in there to do the bias adjustment, and turn it to a fixed resistor. Plus I want to try out bootstrapping the output, as well as adding degeneration resistors in the collectors, or the common emitter points here, as there should be. And what we're going to do is, without the VAS obviously, I'm going to test this output stage. So for clarity, I'm going to now remove the VAS. I'm going to test this output stage. That's supposed to be an N. Oh dear. Yeah, there we go. I'm going to basically test this output stage without the capacitor first, and I reckon around about a 100 mica should be about right. But first, before we worry about that capacitor, we'll get the thing biased and everything and look at it on an oscilloscope, and feed an input signal in here and look at its output with no negative feedback or global feedback before we look at, well, the input stage that's going to be connected to it. Now, granted that this topology with the OpAmp IC is not going to produce a lot of wattage, just bear that in mind. But let's get back to the original schematic. Meanwhile, back at the schematic, so as I said, we're going to test this output stage on its own, and then look at bootstrapping the output. Now we'll notice, moving on, that this feedback network here, which is comprised of this 150k resistor plus this 10k resistor here, that would give us a voltage gain of roughly 16. So I'm probably going to change that to a gain of 23, which is pretty normal for most power amplifiers. So that would be changed to a 22k and a 1k respectively, or a 220k and 10k respectively, either way. We're also, well, I'm also going to knock off that part of the circuit because it's not needed. All this is a high impedance to low impedance source, so it's just a buffer. It's not really particularly needed. We're just going to go straight from this point, which is the volume control, which is now the input, straight into our first OpAmp, obviously via a DC blocking capacitor, and yeah, test it out and see how it performs. But as I said, we're going to look at the output stage first. So because of the transistors I'm going to be using BD139, BD140, and TIP36C and TIP35C respectively for the output transistors. They're not going to fit into the breadboard or socket board very easily, so I'm going to have to solder to the transistors, the output transistors, solder the drivers to the transistors, because the output transistors need to be heat sinked, the drivers do not. The diodes from the bases here, this diode string, will be soldered across the two bases here, because these two diodes really need to be in contact with each of these drivers so that the bias of this circuit here is adjusted when the transistors start to heat up. Once the transistors heat up, the diodes conduct more, the bias goes down. And so therefore does the current flow through the circuit go down, or goes down. I can't even talk. And what that means is it's to try and prevent thermal runaway. So once it starts heating up, it drops the current down to limit the amount of current flowing through the output. But really there should be two resistors here to help combat that thermal runaway problem. So, and we'll be looking at 5 watts each. So I'm going to add them in even though they're not originally on the schematic. And I will eventually draw up the schematic properly before the video is made live, so that we can see all the changes and it makes it look a bit clearer. Also, this TL074 IC is going because, well, we don't need that part. I'm going to change it to an NE5534. I believe it's a NE5534A. So let's have a look at these. These are, I don't know, NE534P. I don't know if you can see that, but it's an NE534P. And this is the low noise version. There's an NE5534N, I think it is, which is the ultra low noise version. But these are like, I think they're about nearly $3-4 each. They are quite expensive for an op-amp, that is. But here's our output transistors. That's the TIP35C. That's another TIP35C and TIP36C. And they're just flat pack transistors, power transistors. But because the lead thickness is so thick, it's not going to fit in the socket board. So what we'll do is I'll assemble the output stage in dead bug style. That is, everything will mount to this heatsink here, and just like this, all the components will be wired between the pins, and it's called like dead bug because things are standing up and facing different directions and it's not neat and it looks like crap, whatever. And it's that's what it's called, dead bug style. So that's what I'll be doing. So first I'll get the output stage all buttoned up here, and then we'll look at testing it on its own. And a short time later, here it is wired up. This is what I meant about dead bug wiring. Here's our two biasing diodes, which are roughly in contact with the two driver transistors, which are sitting here. And the two output devices are mounted to the heatsink. Got some heavy duty hookup wire on the positive and negative sides. And I've got 0.47 microfarad ohm resistors here, 5 watt devices, as degeneration resistors on the collectors. The output is formed here. This capacitor is across the two diodes. This is our biasing adjustment pot, which is a 50k linear, with a 2k2 resistor there, which is connected directly to the positive. And I've set that around to about halfway. And reading the original description of this particular circuit, when the pot was set in halfway position, the amplifier performed fine, so it's probably not even necessary, but we'll have a look at how that pot affects the output stage. So what I need to do now is hook this up to a power supply and an oscilloscope. It's going to be a bipolar supply, plus minus, and the zero, or the center point of the power supply, will be our common ground to the output position here. That's all I've got to say about that right now. So without further ado, let's hook it up to the supply and an oscilloscope and have a look at what happens. The Zobel network, which is the 10 ohm resistor and the 100 nanofarad going to ground off the output here, is removed. It is necessary to prevent the output stage from going into oscillation, and we will probably see it going into oscillation on the oscilloscope. So anyway, let's hook it up and see what it does. Alright, I got everything set up. I haven't got a DDS connected or anything yet. I've just got basically the output stage connected to the power supply. Power supply set to plus minus 18 volt to start with. Current limited down to about 500 mA, just in case it decides to start drawing shitloads of current. Got times 10 probe across an 8 ohm dummy load across the output, with the ground being common to the centre of the power supply. Got the oscilloscope in the background there ready to measure at 1 volt per division. Not that we're going to see much at the moment. So I'm just going to turn it on and hopefully nothing goes bang, and if it does, well, it's captured on film. Here we go. Well, it says we're at current limit. And now that I've taken the current limit off, we're not actually getting much in the way of current draw by the looks of things. Not that I can see. That feels alright. That feels alright. If I touch the base, can't see much. So let me hook up a DDS and see what happens. So I've got the DDS set to 1 kilohertz 1 volt. I'm going to turn the load on and see if we get an output. Hopefully, well, we won't if the screensaver activates. We don't appear to be having any output at all. Okay, change that back to times 1 probe. We're apparently drawing 60 mA too, but I've got no output on the screen, which is interesting because we should have. Right, let's try that again. For some reason the software stopped responding, so we'll try that again. Now we do have an output, and we can see a lot of ringing. That's a good indication that it's oscillating, and there's also a lot of noise artifacts on the thing here. If we play with the bias, the noise gets worse. In fact, if we turn it right there, the noise goes away. But we've still got ringing there. And as we can see, that is pretty noisy. So, just doing a heat check on the transistors here. They feel fine. Turn the bias down a bit fixes that really scratchy artifact. But why is it ringing like that? Well, the simple answer is because the C-clay or the complementary feedback pair are good for producing high gain, but they're very susceptible to going into oscillation. They're unstable, and the reason why it's probably not stable at the moment is because there's no Zobel network in the mix there. So looking at just the output stage being driven by the DDS, I'm currently at 5 volt peak to peak in at 1 kilohertz. We can see there's a lot of nasty artifacts on the output here, and this is without a Zobel network connected. Now if I play with the bias pot, we can't see too much difference in the signal, but yeah, we can see that by reducing the bias we cause it to flat top. So around about the center is where it needs to be. So what we need to do is connect up a Zobel network to the output stage so we can see if we can get rid of any of these artifacts, which are basically oscillation. So I've got the resistor and capacitor just joined with some jumper cables on the desk here, and if I take my 10 ohm resistor in and touch it to, or connect it to the 2 resistors, and immediately we've got a nice clean signal. Now if we change the bias, we can see that we're flat topping. So the bias pot really doesn't do anything. It doesn't need to be there. we've got very little current draw on the output, on the, well, according to my power supply anyway. So the output stage is, not getting hot or anything, but we're getting a nice clean signal of around about 4.3 volt, roughly peak to peak, going out. So if we reduce the signal input, our output voltage also decreases. We're now about 3.5, and according to the DDS we're at 4 volt peak to peak in. Okay, and I've connected the second channel of the oscilloscope up to the input, or the output of the DDS, but the input of the output stage, and we can see that the signal levels are roughly the same. In fact, I believe the output signal is lower than the input signal. And if we look at the statistics there, we can see the channel 1, which is the output, is 3.57 volt peak to peak, and the input is actually 4 volt peak to peak. So we're about 500 millivolts less at the output. So what does this mean? Not much, not diddly squat. It just means basically the output stage is not going to produce any extra gain or any voltage gain. It's not supposed to. All it does is it changes a smaller current flow into a larger current flow, because to have a voltage of say 4 volt peak to peak out coming out of the output stage, it needs a little bit more current to drive a speaker driver than it would just driving a dummy load like this. So that's the whole entire point of the output stage, is basically a current converter, not actually a voltage converter. So it will not produce any voltage gain, so the measurements we're seeing here is exactly how it's supposed to operate. What you put in is basically what you get out, albeit we're about 500 millivolt difference. So the next step is to breadboard up the OpAmp stage of the circuitry, connect it to our output stage, and actually see, well, what we get. Do we get an amplifier with a fair few watts coming out of it, or is it a complete waste of time? Let's find out. Okay, as messy as that looks, I've got it all wired up. I've just got a simple Zener diode and resistor dropper for both the positive and negative rails to the OpAmp. Hopefully that's wired correctly. We'll soon find out. If anything goes bang, well, it goes bang. We're ready to test it. I'm going to leave it at 20 volt plus minus. Should be enough for the Zener diode to work. I've got the DDS at 1 kilohertz, 1 volt peak to peak. Couldn't think where I was going with that. So I've just turned the current limiting on just to make sure nothing draws excessive current. So I'll turn the load on and hopefully we see an output. We do, albeit bad. And in fact, that looks like absolute shit. That a sine wave is not. I'm not even sure what that is supposed to be. Let's play with the bias pot a little. Yeah, that doesn't seem to be having any effect on it. Either I've wired something wrong or it's not functioning correctly. But yeah, that is the most horrible waveform I've ever seen an amplifier produce. It's like half square wave and then backward triangle. So I don't know what's going on here. Now that could be the Zener diode or Zener diode network here is not actually producing plus minus 15 volt equally. So I could try upping the voltage, and upping the voltage just makes it look more square wave. So I'll leave it at 21.2 roughly. I'm going to see what the voltage is across the pins that it's supposed to be. In fact, I'll turn it off and I'll just make sure that I've actually wired it correctly. Right, so thou shall measure voltages. So I'm just going to measure between ground and positive, so that's ground there, and the VCC pin. Well, can't seem to get a voltage because the wire has come out of the board. That could be exactly why it's not working. Now, I had a pair of pliers here a while ago and they seem to have disappeared, but that wire is not actually sitting where it should be. But that didn't seem to make any difference to the output. But anyway, let's try measuring that again. We should have, well, we've got 10.5 volt at positive, and at negative we've got -6, so that's not actually regulating correctly. Up at the 24 volt, and have another look at my enormous penis. No, the voltage. Got 12 there, and -8 there. So it's not actually operating as expected. So, as usual, using a Zener arrangement as a regulator does not make. Let me make a little modification. Okay, I changed the resistors that I had as the droppers to the Zeners, or Zeners, from 2K7 back to 1K, well, to 1K, to see if I get a little bit more voltage output. But I think I've actually, now it's more square wave, I think I've actually discovered what the actual problem is, and I'll let you in on that secret in a minute. Let me just find out what our voltage is now. Nothing apparently. Absolutely nothing. Well, that sucks. It should be. That's better. I had a shorter capacitor. I've got 13 volt there. And 13 volt minus there. So it's let me change the voltage per division there to say 5 volt. It's very square wave. Well, this capacitor here, which is a 10 microfarad non-polar, that's supposed to be going to ground. Currently it's connected to the negative rail. So instead of being there, it should be there. So I've actually connected that capacitor in the wrong place. So if I unhook that and connect it to the correct place, what's going to happen to the output waveform? Because it would basically like that capacitor's not even in the circuit. Bingo, we now have a sine wave. Isn't that interesting? Okay, so I'll increase my amplitude input. I've done that way too wrong. I want 1 volt. Not 10. Now, at 1 volt in, that's clipping badly. It's not even producing an output. So I'll go back to 500 millivolt. So it looks like our input sensitivity is not that big to get full output. We're looking at 0.5 of a volt, and it's already clipping, and it's peaking out at 10 volt peak to peak. So it's not going to be producing much in the the realms of output. So I'm just looking for where its actual output peak voltage is before clipping. So yeah, 0.5, 0.4. So we're looking at 400 millivolt in for 10.1 out. Okay, so we'll say 5.5, which I believe is 10.1 divided by 2. We can find that out. 10.1 divided by 2. 5.05, I was close. Square that, it's not going to be very powerful, I'm going to tell you that right now. It's 25 divided by the load. 3.1 watts. That is pathetic. Absolutely pathetic. But it is working. just not very well. And it's not producing that much in power output. And according to the description in the project, it's supposed to produce about 18 watts. Nowhere near. Sorry, you'd be wrong. That as a power amplifier is pretty useless. So, OpAmp based power amps, using an OpAmp to drive an output stage. Nah, it's not worth it. Not worth it at all. So something's not right here, because our negative voltage is now, it's dropped to -4. In fact, it's actually dropping significantly. And our positive voltage is 8. So I do not know what is going on. So I'll back the input magnitude off to 100 millivolt. Yeah, it's like 6 volt now. -3. Wow. Okay. Yeah, that's real good. That is. Turn it off. Turn it back on again. Let's have a look at that voltage again. 6 volt there. 3 volt there. That is perplexing. It's dropped right down, and I don't know why. So the issue is with those Xeno diodes. It's come on. With those Xeno diodes, it's not functioning correctly, because the voltage is just starting to really drop off, and I don't know why. Because we're only drawing about an average of 150 mA at the moment. So if I up that output of the DDS up, yeah, it's clipping way earlier now. We're now at 300 millivolt for a clean signal. But that's not right. Should be able to be pushing out more than that. But considering our supply voltages to the OpAmp are really low, it ain't gonna do shit. I mean, we've got apparently 11 volt there now on the positive, and 9 volt on the negative. But that was after I increased the input voltage to the OpAmp and got the OpAmp to do something. So this Xeno diode rectification idea is not going to work. So what do we do about that? Well, why don't we actually just try plus minus 15 volt regulators? Okay, so I've got a 7815 and a 7915 respectively voltage regulator on both the positive and negative rails now, so we should be getting a good plus minus 15 volt to the OpAmp. I'm at 1 volt 1 kilohertz on the DDS, so I'll turn on the load now. It's still clipping badly. Really clipping badly, which is kind of interesting. And we're drawing 1 amp. Ooh, that's quite significant. So I might actually, it looks like we're oscillating actually. So that's not good. And those transistors were getting red hot, so there is still a problem. So I'm going to disconnect the output stage from the equation here and just have a look at what our voltages are, because I might have one of the things wired incorrectly here. Well, I figured out what was causing it to oscillate this capacitor C5 here, which was originally 100 nanofarad in my circuit, was causing the entire thing to oscillate, and it was drawing over 3 amps of current out of the power supply, even with a 100 millivolt peak-to-peak input. So yeah, I took that capacitor out completely. The circuit's working fine. I also forgot to add this 33 picofarad across the feedback resistor here, but I've done that now. It's cleaned the signal up somewhat. However, the sine wave is relatively clean, yes, but we're still only getting a maximum output of 10 volt peak to peak. So that's roughly about 3 watts of power peak, probably about 1.2 watts RMS, or average I should say. I shouldn't use that RMS anymore, should I? And that's with 400 millivolt in. As soon as I increase the amplitude to say 500 millivolt, it starts asymmetrically clipping and then starts going more square, so it cannot output any more than 10 volt peak to peak, and that's including at the output of the OpAmp on pin 6, which would make absolute sense because your output stage here is not supposed to be producing any voltage gain. All it is a current converter. You're taking a small input current and turning it into a larger output current. So because you're driving a speaker, you need a lot more current to drive the speaker at the same voltage than you do off of the OpAmp, which is why there is an output stage here. Because connecting it directly to the IC itself will not make the IC very happy. It'll work probably for a few minutes, and then it'll just eventually blow the IC because it'll be getting red hot. Now I also had a 100 microfarad bulk filter capacitor across this negative regulator, and it was getting hot, the regulator that is. I couldn't figure out why, and that's because I connected it backwards, reverse polarity, and I basically just blew the arsehole out the capacitor. Just went, didn't go bang or anything, wasn't spectacular. See, maybe or not, that it's starting to bulge there. I had it backwards, that was red hot, it blew, and that was the end of that. Not that it's needed in the circuit anyway, but that's the reason why this negative regulator was getting hot. Now it's mildly warm. But yeah, always check polarity capacitors. Okay, so in the interests of you know, doing a sound test and everything, got it hooked up to an audio source. Got the speaker connected to the output instead of the oscilloscope now. Turn it on. That doesn't sound too good, does it? Got tremendous mains hum. Well, that's exciting, because we're actually now drawing 2 amps of current. So now I've got to fault find what the problem is. Okay, take 2. I must have blew the OpAmp up. Now that seems a little bit more reasonable. 50 mA current draw. Now let's see if music comes out of it. Try that. Well, okay, it sounds reasonable with that track anyway. Anyway, I think I'm going to leave this video here because I'm not really getting any more improvement in the results. I did change the biasing potentiometer to a fixed resistor. So I've actually got two 2.2k resistors in series here, and this join can be connected via a 100 microfarad capacitor back to the output, positive at this junction, negative at the output, to bootstrap the amplifier to give that output stage a constant current source. However, I couldn't see any difference in the results on the output by adding it or not having it. But for what it is, I've got an input sensitivity now of 1.4 volt peak to peak for an output swing of 10 volt peak to peak. So yeah, you're looking at around about 3 watts. However, the results are disappointing, but I've got an output stage now to play with for other amplifier projects, even though it's connected in C-clay pair. I think that's going to do it for this video. The amplifier works, just not as doesn't perform as well as I wanted it to. But yeah, as I say, we're going to leave that here, and I hope you enjoyed this video. And if you did, please remember to rate, comment and subscribe below. And you can almost always follow me on Facebook and Twitter. The links are in the description as usual. Anyway, this is the Astro 30 saying, see ya, have a great day. Still have a relatively clean output signal though, albeit it's not very powerful. Yeah, oh well.